Welcome, everyone. Today, we embark on an exciting journey into the world of data analytics. Our goal is to understand how we can effectively unlock valuable insights and knowledge hidden within vast amounts of data. Let's explore the four fundamental types of data analytics, each serving a distinct purpose in our analysis. These types guide us from simply understanding past events to actively shaping future decisions and strategies. First, we have descriptive analytics, which focuses on summarizing and understanding historical data. This type helps us make sense of past events, providing a clear picture of what has already occurred. Essentially, descriptive analytics answers the crucial question, what happened, by reviewing past data. Next, we move to diagnostic analytics, which delves deeper into the reasons behind specific outcomes. It helps us uncover the root causes and contributing factors for why certain events unfolded as they did. Diagnostic analytics is all about answering the question, why did it happen, with detailed explanations. Then, we have predictive analytics, which uses historical data to forecast future trends and probabilities. This powerful type helps us anticipate what might occur next, based on observed patterns and models. Predictive analytics aims to answer the forward-looking question, what will happen, with reasonable accuracy. Finally, we reach prescriptive analytics, which recommends specific actions to achieve desired results. It guides us on the best course of action, optimizing our decisions for future success and outcomes. Prescriptive analytics answers the ultimate question, what should we do to reach our objectives effectively? Now, let's walk through the typical flow of a data analytics project from start to finish. Every analytics journey begins with a clear problem definition, understanding exactly what we need to solve. Following that, we move into data collection, gathering all the relevant information from various sources. An essential step is data cleaning, where we process and prepare the raw data for accurate analysis. Once clean, we perform data analysis, applying statistical and computational methods to uncover patterns. Then, we focus on visualization and reporting, presenting our findings in clear, understandable formats. Ultimately, the goal is to derive actionable insights that drive informed decisions and create tangible value. To excel in this field, aspiring data analysts need to cultivate a diverse set of essential skills. It's truly a powerful blend, requiring both strong technical prowess and sharp critical thinking abilities. First, a solid foundation in statistical analysis is crucial for interpreting data accurately. This includes understanding data distributions, conducting hypothesis tests, and applying regression models effectively. Next, proficiency in programming languages like Python or R is vital for data manipulation and model building. These languages are indispensable tools for efficiently handling and transforming large datasets. Data visualization skills are also paramount, enabling you to create clear and impactful graphical representations. The ability to visually communicate complex data insights makes them accessible to all stakeholders. Domain expertise is incredibly important, as knowing the industry context helps interpret data meaningfully. Understanding the specific field ensures your analysis is relevant and provides true business value. Finally, strong communication skills are key to effectively presenting your findings to diverse audiences. You'll need to explain complex analytical results clearly to both technical experts and business leaders. Let's explore the typical stages involved in a data project, guiding us from an initial idea to a complete solution. We'll cover the entire journey, starting from the very first concept all the way through to a deployed, functional solution. First, project scoping and planning. Here, we define clear objectives, project scope, and what success truly looks like. Next is data acquisition and integration, where we gather relevant data from various sources and combine it effectively. Then comes data preprocessing and transformation, crucial for cleaning, validating, and preparing our data for thorough analysis. Following this, we move to model development and analysis, applying statistical or machine learning techniques to our prepared data. After analysis, we focus on interpretation and reporting, extracting valuable insights and presenting them in a clear, understandable way. Finally, deployment and monitoring involves implementing our solutions and continuously tracking their performance over time. Now, let's discuss the core principles of data ethics, which are fundamental for responsible data handling. These principles are essential for ensuring that all our data practices are both responsible and fair to everyone involved. Data privacy is our first principle, focusing on the protection of sensitive information. This means safeguarding personal and sensitive information from any unauthorized access or misuse, which is absolutely critical. Transparency is another vital principle in data ethics, promoting openness in our processes. It means clearly communicating how data is collected, how it's used, and how we analyze it. Fairness and bias ensure that our data practices are equitable and unbiased. We must ensure that our algorithms and analyses do not perpetuate or amplify existing biases, promoting fairness. Accountability is key to responsible data practices, ensuring someone is answerable. This principle establishes clear responsibility for data handling processes and the outcomes of decisions made. Lastly, data security is paramount for protecting our valuable information assets. It involves implementing robust measures to prevent data breaches, unauthorized access, and any form of misuse. Let's delve into some fundamental statistical measures that help us understand our data better. These measures are crucial for quantifying both the central tendency and how widely our data is spread. First up, we have the arithmetic mean, a very common way to find the average. The formula for the sample mean, x bar, is 1 over n times the summation from I equals 1 to n of x sub I. Here, x bar represents the sample mean, which is the average of your observed data points. The variable n denotes the total number of observations or data points in your dataset, and x sub I refers to each individual observation or data point within your collection. The sigma symbol, represented as the capital letter S, signifies the operation of summation. The mean essentially represents the average value of all the observations within a given dataset. You calculate it by summing all data points together and then dividing that sum by the total count of points. It is important to remember that the mean can be significantly affected by extreme values or outliers. Next, let's explore the standard deviation, a measure of data dispersion. The formula for the sample standard deviation, S, is the square root of 1 over n minus 1 times the summation from I equals 1 to n of x sub I minus x bar squared. Here, S represents the sample standard deviation, indicating the spread of data points. Again, n refers to the total number of observations or data points in your sample, and x sub I still represents each individual observation within your dataset. Finally, x bar, as before, denotes the sample mean of your dataset. Standard deviation measures the average amount of variability, or how spread out the data points are. A low standard deviation suggests that the data points tend to be very close to the mean. Conversely, a high standard deviation indicates that the data points are spread out over a much wider range. Now, let's explore essential data cleaning techniques using Python's powerful Pandas library. These are crucial steps to properly prepare your data, ensuring it's ready for accurate and meaningful analysis. First, we'll look at effectively handling missing values, a common challenge in real-world datasets. The FILNA method is used to replace missing values, often represented as n, ensuring complete data for analysis. This code snippet demonstrates how to import pandas, create a dia-tia frame with missing values, and then fill them using the mean of column A. Next, we'll learn about removing duplicate rows, which can skew our analysis if not addressed. The drop duplicates method efficiently identifies and removes redundant rows, preventing skewed analysis from repeated entries. This example shows importing pandas, creating a dia-tia frame with duplicate rows, and then removing those duplicates to get unique entries. Finally, we'll cover correcting data types, ensuring our columns are in the appropriate format for operations. The astype method is used to cast a column to a specific data type, which is vital for correct calculations. Here, we import pandas, create a DATIA FRME with a column of string numbers, and then convert that column to integers, printing the new data types. All right, class, let's now wrap up our introduction to data analytics with a concise summary of our key learnings. Here are the most important takeaways from our discussion that you should definitely remember going forward. Remember, data analytics is all about transforming raw, unprocessed data into clear, actionable insights for decision-making. We explored its four main types: descriptive, diagnostic, predictive, and prescriptive, each serving a unique purpose. The process involves clearly defining problems, then collecting, cleaning, analyzing, and finally reporting your data findings. Essential skills for success include a strong foundation in statistics, programming, data visualization, and domain-specific knowledge. Always prioritize ethical considerations like ensuring data privacy, promoting fairness, and maintaining transparency in your work. Finally, Python, especially with powerful libraries like Pandas, is an excellent tool for effective data manipulation and cleaning.